Hello and welcome to the next page. We're talking about boundary value problems. And so in boundary value problems, the dependent variable and its derivatives are specified at different points. So we're given a differential equation and then we're going to subject it to two different initial points. We're going to say y of a is equal to y sub 0 and y of b is equal to y sub 1. So for our solution to our differential equation, we have two initial values. So that means that our solution, that our equation has to go through both points. So over here on the side, you see that here is the family of solutions for the differential equation. We want to find all solutions that go through both points. So in this case, for this specific example, there's actually two solutions that go through both initial values. All right, so we're not really here for this section talking about a uniqueness of solution. Here for the boundary value problems, it's based off of, okay, we have two initial values and we're trying to find, what is the solution to this differential, or the solution or solutions to the differential equations that have the same initial values. All right, so example 3. The given two-parameter family is a solution of the indicated differential equation on the interval from negative infinity to infinity. Determine whether a member of the family can be found that satisfies the boundary conditions. All right, so there are many things that can happen. There could be no solution. Right? We could have no solution to our differential equation that goes through both points. We could have one solution, we could have two, we could have three, we could have an infinite amount of solutions. And so what we're doing is we're just going to check. And that's my daughter playing with a toy outside. So example 3. So we're just going to check. Here we're given the solution to our differential equation. And then we're given the differential equation, which is going to be a second order linear differential equation. So we're going to go ahead and check C. All right, this one we're not checking for existence and uniqueness because this is a boundary value problem. All right, so we're going to go ahead and substitute in. So we're going to first put in our initial value. Y of 0 is equal to 1. But I'm going to go ahead and substitute everything in for x. So c sub 1 e to the 0 cosine 0 plus c sub 2 e to the 0 sine of 0. And this should equal 1. Well, when I do all the math to the left, e to the 0 is just 1, cosine of 0 is just 1, plus sine of 0 is 0, so 0, so that all equals 1. So we find that c sub 1 is equal to 1. Now, let's go ahead and plug in the second value, which is pi over 2. All right, and so now we're going to go ahead and say c sub 1 e to the pi over 2 cosine of pi over 2 plus c sub 2 e to the pi over 2 times sine of pi over 2. And this should also equal 1. Well, the left side, cosine of pi over 2, is just going to be 0, plus c sub 2 e to the pi over 2. Sine of pi over 2 is 1, so that equals 1. So c sub 2, I'll divide that e to negative pi over 2 to the other side. So 1 divided by e to the pi over 2 is just e to the negative pi over 2. So then that gives me my solution as y equals 1, y equals e to the x, cosine x, plus e to the negative pi over 2, e to the x sine of x. In this case, we had one solution that went through both points. Let's go ahead and do D. So when we're doing D, we're going to do the same thing. We're going to plug in our conditions. Y of 0 is equal to, go ahead and plug in. We get c sub 1 e to the 0 cosine 0 plus c sub 2 e to the 0 sine of 0. I've done this one, but in this case, we're setting it equal to 0. So we have c sub 1 plus 0 is equal to 0, so c sub 1 equals 0. All right, now let's do our next part. Y of pi. So plug that in. C sub 1 e to the pi cosine pi plus c sub 2 e to the pi sine pi. Well, sine of pi is 0. And then cosine of pi is negative 1. So we have negative c sub 1 e to the pi. But if negative c sub 1 e to the pi is equal to 0, then c sub 1, again, equals 0. So when we write out our solution for D, we're going to say, well, y is equal to, if c sub 1 is 0, that whole first term is not there. So we just say c sub 2 e to the x sine x, where c sub 2 can be any real number. So here we have an infinite amount of solutions. Just remember, for boundary value problems, we're not looking for uniqueness like we did on page 1. Here we're just trying to find the solution to our differential equation of a higher order of what we have been working with. Again, here you see it's a second order linear differential equation. All right. Now, talk about homogeneous or homogeneous equations. So say we're given a sub n, x, d to the n y. So say we're just given a differential equation, of the nth order, and it's linear. All right. Well, if we're given a linear differential equation, and that's set equal to g of x, all right, that's just going to be a linear equation. If g of x equals 0, so if that equals 0, if we had a linear differential equation, second, third, fourth degree linear differential equation, and it's set equal to 0, it's said to be homogeneous. All right, and then those are pretty easy to solve. If it's equal to some function, so say it's not equal to 0, it's equal to like 5 or 2x or 3x plus 2, it's non-homogeneous or non-homogeneous. All right. Now those are a little bit different. We're going to solve them very similar to a homogeneous. That just is an added extra step or two. All right. So some assumptions that we're going to now assume throughout this course is that all of our coefficients for our differential equations are going to be continuous on an interval that we're using, and also g of x is going to be continuous. And for the interval that we are using, a sub n of x, so that leading coefficient is not going to equal 0. All right. Now, that just, instead of having to always check, we can always assume those. So, another way to write a differential operator, usually we, write it dy over dx. Well, now we can use the letter d to denote, okay, this is the derivative. So, that's a first derivative. D squared y, that's going to be a second derivative, and so on and so forth. All right, so that's just another way of saying, hey, I'm taking the derivative. So when I'm looking at, here I'll say at the very end of this. So we're going to do a little bit of the third page as well. We define an nth order differential operator or polynomial operator to be L is equal to, and then our differential, all right, where L possesses the linearity property, which means that our differential equation is linear. So, instead of up here, let's try to, I'll just do an example. If we have this, all right, for our differential equation, we can just now write, because it's a linear differential equation, we could say L equals 0 for our differential equation, knowing that our differential equation is linear. So we could just replace the whole differential equation with an L to show that it's a linear differential equation. All right, now, talking about using that operator, any linear differential equation can be expressed in terms of D. For example, we have y double prime minus 7y prime plus 3y equals 10x plus 1. We can rewrite this as d squared y minus 7 dy plus 3y equals 10x plus 1. Now, that's just another way to write the differential equation.